9 o'clock. Well, good morning. My name is Matthew Selby. I'm with Elpro Technologies. Myself and Brian Cunningham, System Engineer at Elpro Technologies, will be giving a presentation on RF 101 and basic installation best practices. Just a brief history. Myself started Elpro about a month ago on April 6th. I've been in the business for about 15 years. Former U.S. Marine, participated in Operation Desert Shield and Desert Storm back in the early 90s. I currently reside in Tampa, Florida, and handle the Eastern region for Elpro. Contact information is below, and if you have any questions, just feel free to stop me when I'm presenting, and we'll address that question immediately. Just a brief history on Elpro real quick. Elpro's been around since 1983. As you can see, it's changed hands several times. Lastly, about a year and a half to 2 years ago, group that owns Aquamonics out of Australia acquired Elpro, and that's where we currently sit today. Right now, it's myself handling the East Coast. JL Betts is the VP of Sales. He's based in Bakersfield, California. And Brian Cunningham is in British Columbia. He is our systems engineer. I'm sure most of you, if you've had a technical issue with any Elpro device, you're probably talking to Brian. He's been with Elpro pretty much since the inception. I believe he came on board back in 2007.
Oh yeah, thanks, Matt. Yeah, it's been quite a journey here.
Fantastic. Just a quick history of wireless. I picked out a couple of key dates. 1899, Marconi sent the first international wireless message from Dover, England to Wearmere, France. 1941, Hedy Lamarr, and we'll discuss her just a little bit more. She put a patent in 1941 that pretty much invented or patented spread spectrum frequency hopping. This was very crucial during the Cuban Missile Crisis back in the early 60s. 1978, AT&T Bell Labs tested the first mobile cell phone system using cellular, and the World Wide Web was developed and put in place in 1990. So again, just a quick history of wireless. As I mentioned before, the invention of spread spectrum. This was patented by Hedy Lamarr, the famous actress, back in the 40s. This was designed to be immune for interference. And with the frequency hopping, the message and the data being hopping from frequency to frequency in the 900 space, it made it difficult for enemy eavesdroppers to hack the messages and interpret, eavesdrop on transmissions with the U.S. forces. So what we talk about is choosing a radio frequency and how to create a network. So the first thing you want to do when you're creating your network is determine what frequency you want to operate that network in. Two takeaways from this: you can go far in a wireless network, or you can go fast. You can't do both. As you can see down at 150 megahertz that Elpro has product in this space, this goes tremendously far. However, it's got a very limited amount of bandwidth or throughput that you can transmit that data from point A to point B. As you grow up in speed, your data rates can become larger. You can push a lot of data through that same pipe, but you can't go far. So again, the biggest takeaway from here, depending on your frequency, the lower the frequency, the further you can go. The higher the frequency, the faster you can go. You can go fast or you can go far. You can't do both. Next, you want to choose whether it's a licensed or unlicensed frequency. Unlicensed radios are free to use after the hardware cost, so there is no licensing fee. You do not have to coordinate anything with the FCC. Those frequencies that you can operate in that were called license free or unlicensed are the 902 to 928, the 2.4 to 2.4835, which is Wi-Fi, or 5.17 to 5.835. Also a newer Wi-Fi spectrum. You typically see this in a lot of video surveillance networks, short range, high bandwidth, again, unlicensed. The licensed radios, these require a little bit more work on your end at initial setup. They do need to be filed with the FCC. Typically, a license runs about 10 years, and depending on the frequency, ranges about $1,000 for that 10-year license. Now, the beauty of this is that you own that frequency. When you file that with the FCC, the the area that you want to utilize that frequency in is dedicated to you and only you. No one else can occupy that frequency. So you have absolutely no interference by utilizing that frequency band that you have filed with the FCC. Less interference, and in some cases there'd be absolutely none at all. This is limited by the rules of the FCC, so there are certain rules that you need to play by within that frequency as far as power that you can emit from each site, and we'll get into that in a little bit later. Some of the products that Elpro offers in the licensed frequencies, the 150 megahertz, the 435 to 470, and also in the 900 megahertz space. Throughput, I mentioned this before. Throughput is how quickly data can be pushed through a connection. How far can you get that bar? How fast you get that packet from point A to point B. This is usually determined by the channel width. And as I mentioned before, channel width is also determined by frequency. And it is affected by the signal strength and noise. And noise, what I'm referring to there, is others that play or have equipment in that space or frequency that you're currently operating in. That could also create some connectivity issues, causing interference wherever that system, radio, or network may reside. The wider channels can accommodate higher throughputs, but they also allow them more susceptible to noise. So the wider the channel, the more ability it has to absorb other radios or other networks within that area, causing interference, and it could cause issues with connectivity as well. But the throughput is the ultimate network test for most cases of how reliable your actual link is. This is just a quick snapshot of an iPerk test that Brian had done. In this particular situation, from point A to point B, we're getting just shy of 4 megabits per second throughput. Spectrum basics. In 1980, the FCC authorized the unlicensed use of spectrum devices in the 915 megahertz, the 2.45 and 5.8 bands, also known as the ISM bands. There are two types of spectrum. There's frequency hopping and direct sequence. Frequency hopping, if a packet is not received on one frequency, it is resent on another frequency to make sure that it is received on the other end. By this, it does allow for lower throughputs, but you can go further distances. The other is direct sequence, or DSSS. In a high noise environment, the reliability of the data is dependent upon the signal to noise ratio. There are limits to the amount of noise in a bandwidth that DSSS can handle. If there's too much noise on a given frequency, communications will fail and they will not work. You can get higher throughputs, but you can't go as far. DSSS is typically what we see in your Wi-Fi networks, your home Wi-Fi, public Wi-Fi at the local Starbucks, McDonald's, whatever the case may be. Those are just examples of frequency hopping and direct sequence. With the ranges of antennas, I'm going to turn this over to Brian real quick and let him go over some expected distances with certain antennas. Brian?
Yeah, thanks, Matt. So in this chart, we've got what we're showing is some typical ranges that you'll get with our 900 megahertz frequency hopping 1 watt radios. Now keep in mind, we're going to show another couple of slides showing a 900 megahertz direct sequence spread spectrum, and then we're going to show some other frequencies. Now these are just sort of ballparks that if a customer called up and said, I have a 1,000-foot range and I don't have line of sight, it's densely obstructed, like what we'd see at maybe a refinery or a chemical plant. This is sort of a guideline based on experiences of, literally hundreds of site surveys of traveling around the countryside, plugging in, powering up our radios with our portable test kits, and seeing just how far we can go. So with 900 megahertz with a frequency hopping 1 watt radio, the cutoff point for where these radios generally require line of sight is about 2 miles or 1,000 feet. So in the obstruction column, if you see LOS, that stands for line of sight where one antenna can see the other antenna. Now in the middle column, describing which antenna, the main takeaway from this is that as the distance gets greater and greater, or the obstructions get more and more dense, the antenna has to get higher and higher gain to accomplish the greater distances. Then if you look in the far right-hand column, the typical antenna height, as you can see, as the radios get farther and farther apart, the antennas need to be located higher and higher above ground. So in the antenna column, we're showing the gain of the antenna, and we're showing a couple of different model numbers of some of the antennas that Elpro offers. And then in the column right next to it, you can see the cable has a negative number associated with it. So the antennas have gain, they boost the signal, and the cables have losses, they subtract from the signal. So this is where you can see we've boosted the antenna gain higher and higher. And of course, we're going to lose more and more of that signal in the coax cable. So we've compensated for that with a higher gain antenna. Now with a 900 megahertz frequency hopper, you can go, the maximum range is 20 miles, but of course the antennas have to be higher and higher above ground. So we have fewer customers that are willing to do so, because in some cases that may require them to erect a 100-foot tower or something of that extreme. So these are just sort of ballparks to start out, sort of guiding points as to how far is easily accomplished and what are typical antenna heights there. Okay, Matt, let's go to the next one here. Okay, so here we're showing a direct sequence 900 megahertz radio. In this example, we're using our 945 UE. That radio is a Ethernet pass-through modem. So essentially, whatever you put into the Ethernet port of one radio comes out the Ethernet port of the other radio. And this is the unit we would use for high-speed throughput applications like wireless video. So as you can see when we look at the distance column on the left-hand side, we can see the distances are getting quite a bit shorter. And then we're going up to just 5 miles in this example here. But with this type of radio at a distance of 1,500 feet, that's generally the cutoff point where you have to have line of sight. So with the direct sequence spread spectrum radio, the signal needs to be quite a bit stronger, and that's why the distances are going to be quite a bit shorter for the same given antennas. Okay, Matt, let's head to the next one here. Okay, now this slide shows the same chart, but at a different frequency, this time at 2.4 gigahertz. And this is assuming our 245 UE. That radio is, again, it's a direct sequence radio. It's a high-speed, high-throughput radio designed for, wireless video or connecting Ethernet networks together, that sort of thing. And here we can see that the distances get even shorter now. And with a 2.4 gigahertz radio, roughly about 1,000 feet at that point, we need to have line of sight to be able to maintain our throughputs. So as you can see with these, as the frequency gets higher, you can see the distances are getting shorter. and we also have to use some pretty high gain antennas to be able to shoot across these distances here. Okay, Matt, let's go to the next one. Let's have a look at 5 gigahertz now. So now we're looking at essentially the same type of radio system. It's a high-speed Ethernet radio, but this time operating at 5 gigahertz. So here we can see we start off the distances at just 50 feet. And then as we ramp things up, we get up to 250 feet. And that's generally where we would say we need to have line of sight. Now, one thing to sort of emphasize here is that these are guidelines, you know, depending on the density of the obstructions separating the two antennas, really determines whether the radio link will work. Now, when we're out in the field and, you know, we've got obstructions like we got drywall and houses and trees and things like that separating two antennas, that's where the folks at Gilson have test kits with radios built in, and they can come out to your site and actually test what the radios, what sort of throughput the radios will actually deliver in your exact environment. So again, these are typicals to confirm these distances in each specific unique environment. That's why we have test kits where we can change out different types of antennas and maybe hike that antenna an extra 10 feet taller and see if we can get proper reception. So that's how we confirm the radio links, is by using one of our site survey test kits. Okay, so let's head to the last one here, Matt. And now this is dropping down in frequency. This is showing a 450 megahertz 5-watt licensed radio. Now, in the 450 megahertz realm, the FCC can give you up to 5 watts of transmit power, and combined with a lower frequency means you're going to get tremendous range out of this frequency of radio system. So now we start off 2,000 feet, densely obstructed, piece of cake. This type of radio can easily shoot through tons of different types of obstructions here. And then as we bump it up, even at 2 miles, we don't need to have line of sight for this type of radio. 3 miles, we don't really need to have line of sight either. It's until we get to approximately 5 miles that this type of radio likes to have line of sight from antenna to antenna. But 450 megahertz tends to curve with the terrain. So it's an excellent frequency to use when you've got hills and trees and other types of instruction where the 900 or the 2.4, the higher frequencies, just simply won't do the trick here. Now, the maximum range with a 450 megahertz radio is about 50 miles. But keeping in mind the shorter ranges are always easier to do because you don't have to have the antennas as high above ground. So, you know, 3, 5, 10 mile radio lengths, very, very common at this particular frequency. Now, keeping in mind, as Pat mentioned earlier, with the licensed radios, the FCC only gives you a fairly narrow slice of spectrum. So the throughput is going to be much lower than the direct sequence radios that we looked at. This is going to be much more comparable in terms of throughput to a frequency hopping spread spectrum radio. Okay, Matt, I think that covers these slides, and back to you.
Thank you. Before I move on into deeper dive of the antennas and installations, I just want to pause for a quick second, see if there's any questions. I know there's a lot of material that Brian just went over from distances. Do we have any questions?
Yep, Matt, we do have a couple questions. First one says, I assume even at 150 megahertz, is still, okay, I assume even at 150 megahertz is still fast enough for sending I/O. For Ethernet communications, I would guess you need a higher frequency or a greater bandwidth?
Yes, that's absolutely correct. 150 megahertz can easily send I/O signals like 4 to 20 milliamp signals or discretes. If you think about a 4 to 20 milliamp signal, once you run it through a analog to digital converter, it really is just with 16-bit resolution, it's only 2 bytes of data. Comparing that to megabits per second, which is what we're looking at for wireless video or connecting networks together. So yes, I/O has a much lower throughput requirement, so we can do it with any of the fixed frequency, the 150, the 450, or the 900 megahertz frequency hopping radios.
Okay, second question we have here is, does it hold true that with wireless, height is might, meaning the higher you have the antenna, the further the transmission capability as a wireless signal falls?
Yes, that is correct. I've heard that expression before as well. And for example, with our 900 megahertz frequency hopping spread spectrum radios, we know the maximum range is 20 miles. So it simply becomes a question of how high does each antenna have to be mounted above ground to accomplish that distance. So yes, that is absolutely correct. The higher the antenna is mounted above ground, the greater the range is going to be.
Next one we have here is, do different types of obstructions matter more than others, or is anything in the way of the signal a problem?
Well, yes, the nature of the obstructions do influence things. If you could think about it as it is the density of molecules separating the in between the two antennas. So if we're in outer space and we have a complete vacuum, these radios will travel thousands, literally millions of miles because there is nothing to attenuate the signal. Here on Earth, air molecules represent an obstruction, so we have a limited range because of attenuation due to air molecules. And of course, as the obstruction gets more and more dense, so we're talking a couple of trees, a couple of houses, maybe a big forest of trees, and maybe an entire subdivision. Yes, as the density of the obstructions gets more and more dense, the range of the radio system gets shorter and shorter. So yes, the type of obstructions do matter a little bit. And there's one special case, and that is conductive metals. These metals tend to reflect radio waves and will contain them. So when we're in a refinery environment or a chemical plant, we've got all kinds of metal obstructions all around. That's where we often want to use an omnidirectional antenna that Matt's going to talk about in a couple of minutes here. The omni antennas radiate 360 degrees so that the signal can come from anywhere. So these radio waves will bounce off of tanks and steel bulkheads and things like that and scatter around a facility. And that's where we want to use an omnidirectional antenna because we don't know where the signal will be coming from. So a couple of little tips and tricks, but at the end of the day, that's correct. The types of obstructions do make a difference. And again, that's why the folks at Gilson are very well equipped with demo kits to be able to confirm that niche, unique environment.
Next one is, do these radios use signal or channel aggregation to increase speed?
No. There's a number of rules that the FCC specifically stipulates that we have to follow. And in this specific case, no, we do not use that technique for transmission.
Second to last one we got is, what type of coax cable is being used? I'm assuming that was for the charts that you guys were showing for the antennas.
Yeah, the coax in the examples in the slides is a type of coax called cell foil. It's similar in physical characteristics to RG58 coax cable, except it has much lower losses. So it has essentially the same flexibility and weight, but much lower losses. But as far as coax cable goes, we're going to talk about that in just a couple of minutes coming right up.
And the last one we got is, will a different frequency help with interference from high voltage?
No. We've done a ton of work around high voltage facilities in electrical utilities. And at the end of the day, when your electrical power comes at you at 60 hertz, any harmonics that it would be generating up at 150 megahertz or 900 megahertz or 450 megahertz are going to be negligible. So no, high voltage power lines do not have any effect on the frequencies we're dealing with.
Oh, last one I heard, just got in, sorry about that. I have heard pine trees are particularly troublesome for radios. Is that true?
That's true for the higher frequencies. At 900 megahertz, by coincidence, it's specifically, we're talking about the pine trees with the 3-inch long needles. I think they might be ponderosa pines or something like that. I forget the exact species, but it is only the pine trees with the 3-inch needles that tend to absorb RF energy quite efficiently. And just by coincidence, they resonate at 900 megahertz, and that makes them a more significant obstruction than other types of trees. So yes, that sounds like somebody who's been out in the field and done a few surveys is asking that question.
And that is all for right now. Thank you, guys.
Thanks, Brian. Antenna basics. An antenna is a device that is made to efficiently radiate and receive radiated electromagnetic waves. It provides a load for the power amplifier within the radio. So a good example is you have your home stereo system. You've got a receiver, a tuner, CD player. You can put those on, you can put a CD in, you can tune it to whatever radio station you want, but you're not going to hear anything unless you have a speaker connected to it. So a good analogy is a speaker to your home stereo is equivalent to an antenna within your wireless network. It's very easy analogy there. Several important characteristics of antennas that you need to consider when choosing the antenna for your application. Brian mentioned antenna gain, the directivity of that antenna, the radiation patterns and the type of antenna, and the polarization of that particular antenna. And we're going to get into that here in the next couple of slides. Antenna types. There are many different types, but primarily what we're going to use are either an Omni or a Yagi antenna. Yagi antennas, they consist of an array of independent elements to focus the radiated power in one general direction. The directional antenna, Yagi antenna, they're classified or used simultaneously in the same nomenclature. The number of elements that are on a Yagi antenna, as you can see below, will determine the gain or the power of that particular antenna. And as you can see by this pattern here, most of the energy is being radiated in one specific direction. In this particular example, it's heading upward or in a northern direction. Where Omni antennas, they create a radiating pattern that is in a 360-degree area. So you're not going to get the distance as you would with a Yagi, but you're going to get a larger area, circumference. So as you can see here, it's equal radiating from the center of the antenna, both to the east and west, left and right, again, whatever determination you want to use. But it is more of a donut type effect of the radiating signal that's coming off of that antenna. Antenna gain. I'm not going to get into the math here, but antenna gain is the power that an antenna, it's the ratio of the power output of the antenna, pardon me, and is the transmitting power that is a trade-off. So if you double the antenna gain of the transmitting power, you're doubling both gains. And it's the same effect, you've actually quadrupling the transmit power. So if you're doubling the power at point A, doubling the power at point A, you're quadrupling the transmission power. We'll get into that here in the next couple of slides as well. But the takeaway from this, a high gain equals greater distance. To get that greater distance, you need a larger antenna. The bigger the antenna, the more power, the more gain, the greater it can go. Directional, I touched on this briefly with the Yagi antenna. As you can see over here on the right is an example, 4 different Yagi type antennas. The more elements you have, the stronger the antenna will be. As you can see, the main lobe here, this is pointing to the left or west. It's the main direction of this particular antenna. And the gains, for instance, a 16 element Yagi antenna is going to get you 15 dBi or dBd. 9 elements is approximately 12. 6 elements is 9. 3 elements is 6. Again, these are just basic rules of thumb for the size of antenna and the gains you can get from that particular antenna. Next thing we'll talk about is the polarization. Polarization is the orientation of the electromagnetic wave from the source. The two common types of polarization are vertical and horizontal. Polarization is most important if you're trying to get the maximum performance of that antenna. For best performance, you need to match up the polarization of the transmitting antenna to the receiving antenna. Simply said, if you've got a vertically polarized antenna at point A, you want to have a vertically polarized antenna at point B to maximize that connection. One of the questions that was brought up earlier about the cabling. Cabling definitely has an effect on any site. As Brian mentioned, the longer length of cable that you have, the greater the loss or decrease in power that you have at that particular site. This is just a rule of thumb using a standard LMR type cable, LMR 400, which is a 3H cable. At a 25-foot run, you're going to lose about 1 dB of power out of that connection. As you go down or larger in size, up to an LMR 900, at a 25-foot run, you're losing about 0.4 dB or half a dB. So the larger the cable, the less loss you're going to have. The trade-off there is obviously a larger cable is not going to be as easy to work with. One, it's much more expensive, and two, it's just not as flexible. The bend radius of that cable is much less than it would be for an RG58, an LMR 400, a smaller diameter cable. And what we're all trying to come up with here is there is some math when you're putting this together, and you're trying to find the EIRP, which stands for the equivalent isotropical radiated power. And this is just the math that you perform at each given site. So at 900 megahertz, the FCC permits a 1 watt radio. 1 watt is equivalent to 30 dB at the radio, and then an additional 4 watts at the antenna. So the maximum that you can have in a 900 megahertz system is going to be 34 dBm or 2.5 watts. So what would happen if you put a 10 dB Yagi in this scenario? Doing the math, you're going to come up with 38 dBm or 6.3 watts. Way too much power. That means you got too much power coming out of that particular site and could be potentially fined by FCC for having too hot or too powerful of a particular site. The rules of the game. According to the math, the 10s and 3s of the RF math, good rule of thumb, negative 3 dB is equivalent to half the power. If you add 3 dB, you're going to double the power. That's the takeaway here. Again, we got some tenths here. Negative 10 dB, 1/10 the power. Positive dB is 10 times the power. And how this calculation works. On the right-hand side, we've got just a quick reference chart. Negative 30 dB is equivalent to 0.00001 watt. So what we're doing here is we've got final signal strength for this particular receive radio is negative 70 dB. So what we're going to do is the transmit radio is 1 watt. You have loss in your cable, which is negative 4 dB. You add your antenna, that's adding 5 dB. The distance from point A to point B, we're estimating it's going to be negative 100 dB. Your receive antenna, again, is a 5 dB Yagi antenna. Cable loss at that point B is negative 6 dB, giving you a total of negative 70 dB for your calculation. Ideally, you want to find, or you want your network to reside somewhere in negative 65 to negative 85. Again, it will work all the way down to negative 110 dB, but it will be much more susceptible to interference, and you're not going to get the reliability that you would be looking for. So again, your sweet spot is anywhere between negative 65 to negative 85 is a good rule of thumb. The Elpro 915 can transmit a maximum of 30 dB or 1 watt. So let's say we connect a 10 dB Yagi antenna directly to this. We've got no loss in the cable. What would our DIRP be? 30 dB plus 10 at the Yagi, 0 for loss, you're at negative 40 dB. In the previous slide, we know that for every 10 dB of gain, you see 10 times the power of milliwatts. So if we take 1,000 milliwatts times 10, we see that this is equivalent to 10,000 milliwatts or 10 watts. Too high. Another scenario, connect a 9 dB Yagi antenna to the 915U Elpro radio. No loss in the cable again. No loss in our connectors. So we got 27 dB at the radio, 9 at the Yagi, or 36 dBm or 4 watts. Anybody have any questions regarding the math?
Yeah, we do actually have a couple questions here, Matt.
Okay.
The first one is, what is the max cable length for an antenna you recommend?
Well, go ahead, Brian. That it depends on the type of cable and the antenna. Every situation is going to be uniquely different, but depending on the frequency and the cable type, will determine the maximum length that you can utilize in that. Again, you want to take that math equation into consideration when you're putting that up. Is there any more detail on that you have, Will?
No, that is all I have right now. If the person who sent that in could send a little bit more clarification, that would help out. The second question we have here is, the graph for an omnidirectional antennas was not totally spherical. Are there any dead spots in these antennas that could be cured by rotating the antenna?
Brian?
Oh, yeah, sure, Matt. I wasn't sure if you wanted me to cover this one.
Yeah.
Well,
sure.
with an omnidirectional antenna, it's going to radiate 360 degrees, sort of like a lighthouse. A lighthouse on the ocean. So with a omnidirectional antenna, there are not going to be any dead spots except directly above and directly below. So, but we're typically not going to use an omnidirectional antenna if we're, oriented, if we're shooting straight up, if we're shooting vertical, into outer space. So as a general rule of thumb, with an omnidirectional antenna, no, there are not going to be any dead spots. With a Yagi directional antenna, the radiating pattern is just in the direction that antenna is aimed. So in the case of a Yagi antenna, yes, there will be blind spots or dead spots where it cannot pick up, and those are going to be essentially outside of the beam angle of that Yagi antenna.
Okay. Next question here is, do you use / recommend phased arrays of Yagi?
Well, that's that's a more complicated setup. I would probably suggest, in our case, no. There's going to be a handful of applications, probably fewer than 1 or 2%, that can utilize a phased array of antennas, but it's extremely rarely done. I would say, again, 99% of the time, it's simply not necessary to maintain a good, strong signal strength.
Okay. Next question is, you showed a slide with 4 Yagi antennas mounted on the same post. Are these for the same radio or different radios? Would they not interfere with each other?
Yes, that's a good point. That slide is that photograph is illustrative. That photograph came from the manufacturer of the antennas. So no, that photograph does not represent a typical installation, because antennas do need to be separated from other antennas to prevent one radio system from interfering with another. And Matt's going to talk about how far, like how many feet away antennas should be. And that kind of explains why when you climb up onto the roof of a high-rise building, why they have all the antennas spaced out on different corners of the roof, as opposed to them all being in one central cluster, which might be a little more convenient or a little more aesthetically pleasing. But no, antennas should not be mounted that close together. That slide is just illustrative of different antenna gains and the different sizes, how the gain influences the physical size of the antenna.
And the last one we have here is, can I parallel antennas?
Can you parallel antennas? It would be possible. You would need to use an antenna splitter. And the trade-off with antenna splitters is that you lose half the power. So it's possible, but it's usually not necessary. I would say, again, 99% of the time, unnecessary.
And that is all we got right now. Thank you, guys.
Okay.
Okay, back to you, Matt.
Thanks, Brian. Thank you. All right. One of the final steps when you're putting your network together is a site survey. Site survey is a theoretical portrayal of what a network may look like. You pick your antenna, pick your radio frequency. You picked your antenna. You've got your location, and what you can do is using tools like Google Earth, get the GPS coordinates of each individual site, plug that into the software program. We currently use PathLoss is the name of the program, and this can give you a computerized theoretical display of what your network would look like and what the potential throughput could possibly be, your RSSI levels, everything you need to see in a network. Again, this is a theoretical. The only thing this does not take into consideration is noise or interference. There's no way to determine if there's someone else in that area utilizing any type of radio frequency. So it's a good gauge to give you a look of what your network could potentially look like and what type of readings you could get in an ideal circumstance. So the result of some of the tools and features that you get when you do a site survey is going to be a topo map similar to this. As you can see, the black lines represent the path from one site to another. Typically, I know this is not a very clear slide, but triangles represent repeater sites. In this particular case, the black boxes, they represent endpoints. And here, the pink or purple box, this is your head end of your network where everything ultimately needs to get back to. So digging more a little bit into the radiation patterns of antennas, as a signal is sent or received from one antenna to the next, it is radiated, as you can see, in almost a football-shaped pattern. It does not come out as a direct laser beam, as you can see here, from point A to point B. So take into consideration or imagine a flashlight or a telescope. As that telescope is extended, your field of view widens, just as a flashlight would. You shine a flashlight up to a wall. The closer you get, the more narrow or more focused that particular beam gets. The further apart, the wider it becomes. So ideally, to get line of sight, as this is shown here, from point A to point B, the Fresnel zone, which is this oval bubble football type pattern, is characteristic of how an antenna radiates the power. So what you want to try to avoid when you are setting up a network is having anything obstructing this Fresnel zone. And if there is anything that could possibly obstruct this could cause reflection of that particular signal back into itself, again, causing interference and not giving you the optimal throughput that you need for your particular link. Again, just some more examples of what a network would look like. This particular instance, square represents the master or head-end radio. Triangles are repeater sites where you can't get from point A to point B. You have to get a repeater in the middle to get to that ultimate endpoint that you're trying to get, which is represented by the triangle with a circle on this particular network design. Okay, we're going to jump into some of the installation basics. We've gone over quite a few. Proper antenna, coax, lightning arrestor we'll get into in just a moment, grounding rod and grounding wire and clamp, the NEMO 4 enclosure, the interior cables, mounting brackets, and lastly the particular radio that's you're going to utilize at that site. I want to show this picture. This is some things that you definitely do not want to see when you get on a site. This could really cause some degradation in your signal and could be pretty costly to your equipment. This looks like it's just a traditional garbage bag or shopping bag that you got from the local grocery store. Looks like they wrapped this at the connection point and then just tried to secure it with some electrical tape. Well, as you can imagine, there's going to be a lot of water that's going to be allowed to get into this type of setup. Holding water, again, creating some rust that's ultimately going to wreak havoc on this particular site. This is a what not to do for sure. Another, I've seen this more than I care to admit on some of the board level radios or equipment that you see inside an enclosure. They're just take a piece of Elpro, glue it to the back of the board, and stick the other side to the back or the sidewall of an enclosure. Creating electrical static. Again, this could be very, very harmful for your particular equipment inside that NEMA enclosure. We do recommend that all exterior cables are waterproofed using tools similar to this. This is just an example of some 3M product. First, you want to wrap the connectors in a foam or a mastic type tape. Wrap that very securely with electrical tape, and then finally coating those connections with electrical rubberized type of waterproof connecting. Again, just best practices. Better be safe than sorry. One of the questions that Will brought up was antenna display. This, what you see here, is something we do not recommend. It's amazing that this is a real live site. I can only imagine what type of interference they've got going on here. But again, you want to have some separation of your antennas. We'll get into the specifics of that here next. But again, this is an example of what not to do. Again, antenna separation, depending on the frequency that's on one particular tower site or top of a building, depending on the frequency will determine the distance you want to have from one antenna to the next. So first we're going to look at the vertical separation. So for instance, if you've got a 150 megahertz radio at a tower site and you want to put another network sharing those resources at the tower site, you can put you can put a 900 megahertz network in there. Rule of thumb is 32 feet of vertical separation, if at all possible, at a minimum, as not to cause any interference from one network bleeding over into the other. Horizontal separation, horizontal separation, similar to that, using our example of 150 and 900. Horizontal separation from 150 megahertz system to a 900 megahertz system is 320 feet horizontal separation. Again, this is simply rule of thumb as not to shoot yourself in the foot, so to speak, and cause any interference to yourself. So good rules of thumb to keeping your antennas separated at any given site where they would have to share assets, power, top of a building, whatever your situation may be. Mounting guidelines. Antennas need to be mounted up high for Fresnel zone clearance and clearance of any obstructions from point A to point B. You want to mount one wavelength away from any wall. Can't tell how many times I've gone out to a site and see a Yagi antenna pointed right into maybe a grain silo or a water tank. And then right behind it, there's a concrete wall. Or again, the back end of a water tank. As I showed in the Yagi antenna, there is a directional lobe. However, there is some radiating power that's coming out of the back end of that particular Yagi antenna. And if that is mounted up against a wall or a water tank, for example, that could possibly radiate or reflect that signal coming out of the back end of the Yagi off of that obstructed material, again, tank, wall, whatever the case may be, and put that back into your directional radiation pattern of that particular antenna, causing some bleed over or self-interference. So you want to have some good clearance on the back end of the antenna as well. Just as you need it in your Fresnel zone, you want to try to avoid anything that could potentially be in the way. Raise that antenna up a couple of feet to clear those obstructions. You don't want to have anything at the tail end of your antenna as well. Lightning arrestors. Briefly touched on this before. This is just a precautionary measure, highly recommended in any site. What a lightning arrestor does, it prevents electromagnetic pulses generated from lightning or any other device that may cause a spike within that electromagnetic area around your device, protecting your equipment. You catch a lightning strike, it's much more cost effective for a lightning arrestor to absorb that energy as not to pass it on to your radio equipment and potentially blow out your radio device. Again, it's a precautionary measure, protecting your equipment from any electrical impulse. Just a quick run through of the Elpro product line. We've got our product broken up into 4 particular groups. We've got the remote I/O, gateways, Ethernet, and serial radios. As we mentioned earlier, we operate in UHF, VHF, 100 and 400 megahertz. We've got devices in the 2.4 and 900 megahertz, both licensed and licensed. And just a quick snippet of some of the products we've got coming down the road. Our 465.4, which is a 4G LTE cellular Wi-Fi modem and router. That should be coming out within the next 60, 90 days. Unfortunately, the COVID experience has delayed production of a lot of our equipment, but it's not just us, that's globally. So as we get more information as to the availability of this, we'll keep everyone informed. And another product we have is a battery operated UHF VHF device in a NEMA 4 enclosure such as this. Applications that the Condor series board level product inside this enclosure. Great for water, wastewater, solar farms, oil and gas. Again, there'll be more information of this as this becomes available. Again, this is probably another 60, 90 days before this is released. And with this particular device, this is kind of a spin-off device from the parent company Aquamonics out of Australia. They do environmental monitoring, mainly in floodwater areas. Sensors connected to this device, sending a signal back to the appropriate folks, letting them know your river is at this certain height, evacuation may need to take place, or we need to open or close a particular gate of a dam, whatever the case may be, more environmental monitoring. This should be available sometime mid to late June. And these are some of the devices that will be in this particular A2 device. It's a combination of VHF radio, cellular. We do offer a cellular gateway that we can mount on the door. It could also be a Wi-Fi device if you want to get Wi-Fi connectivity locally. So you wouldn't have to get out of your vehicle to plug into the network locally. You'd be able to connect with the proper credentials and access that particular site via Wi-Fi from either your phone or laptop. So in conclusion, I hope everyone got a little bit better understanding of the RF basics when choosing a frequency for your network, some antenna properties, and installation best practices, and just gave you a sneak peek of a couple of the items that Elpro has on the calendar for release sometime midsummer. Any questions?